Hi, my name is Marc Brown, and I'd like to show you the Zeus algorithm animation system. Zeus is implemented on a 4-processor Firefly workstation developed by my colleagues here at DEX Systems Research Center. Zeus is noteworthy for its use of parallelism, color, and sound. In order to let you concentrate on Zeus and not on the algorithms being animated, I'm going to use some really elementary sorting algorithms. Keep in mind, however, that Zeus is domain independent, and in fact it's been used for animating some rather large and sophisticated real algorithms. Let's take a look at Zeus in action now. As our first warm-up exercise, let's consider insertion sort. Recall that insertion sort works by examining each element of the array and putting it into place relative to those elements which have already been sorted. In this fairly common and popular representation of sorting algorithms, each stick represents an element of the array. The taller the stick, the larger the element. When the array is all sorted, the sticks will go from short to tall, from left to right. We're now looking at bubble sort. Recall that bubble sort works by making passes through the array. Anytime that it sees two elements out of place, it simply swaps them. In this way, the largest remaining element gets moved to the right, and all other elements get moved one notch to the left. The top view, the dots view, is just showing the tips of each of those sticks. Here, with a relatively small amount of data, the dots view isn't all that interesting. However, when we run a sorting algorithm on a large set of data, the dots view become quite important. Here we're going to be looking at quicksort. Quicksort works by partitioning up the array into two parts, one part that's larger than some value and the other part that's smaller than some value. Quicksort then recursively processes each of the two halves. In the dots view, especially when I change the window to have a square aspect ratio, you can see quite dramatically the various subfiles that are awaiting processing. Let me bring up another view of quicksort, the partition tree view. And over here, we can see the subfiles awaiting processing as rectangular boxes. And you can see the algorithm splitting up the boxes, processing them, and then moving on to another box. The view that I just brought up now is showing a system watch tool. It's displaying how many of the 4 processors we're actually able to utilize. You can see that we have about 3 processors pretty well used. The algorithm itself is sequential. However, each of the 3 views is being updated in parallel by the Zeus algorithm animation system. We're now watching a naive parallel implementation of quicksort. After the elements have been partitioned into 2 groups, the partitioning thread recursively sorts one group, while a new thread is forked to sort the other group. Each thread has been assigned a unique color, and dots are colored to reflect the elements each thread is processing. Watch now as a thread in purple partitions up a subfile and will fork off a new thread, shown here in red, to partition up to work on the left side, while it will continue working on the right-hand side. The view at the right, the partitions view, will color each subfile that a thread processes. The horizontal axis of each colored rectangle reflects the position of the elements in the original array, while the vertical axis gives a range of the values of the elements in the subfile. Note how the color captures a history of the algorithm's execution. Below that, we have the partition tree view that we saw before. It displays a very different perspective of the algorithm. Subfiles that are awaiting processing are displayed as horizontal boxes, while the partitioning elements are nodes in the tree. While a subfile is being sorted, the partition element node and the edge to its parent are displayed in red. They change to blue when the subfile is finished being sorted. Let's now run quicksort on a smaller data set, and I'll introduce an audio view. The pitch of the note will reflect the number of active threads. I'll now bring up the system watch tool. This naive parallel implementation is somewhat over-aggressive in its use of threads, as the Firefly workstation has only 4 processors. Note that those 4 processors are being used to capacity. Let's now listen to some of the other ways we've used sound. First, consider insertion sort. Here we play a note whose tone corresponds to the value of the element being examined. Listen how each new element is trickled into place relative to those which have already been sorted. We'll use that same audio representation in bottom-up merge sort. At the risk of stating the obvious, the algorithm works as follows. It makes passes through the array of elements. The first time, it compares adjacent elements and swaps them if necessary. The second pass, it merges the pairs into a sorted group of 4. Then, the next pass, it merges the groups of 4 into 8s, then 8s into 16s, and so on. Now let's listen to bubble sort. We're playing a note as an element moves to the right. As before, the pitch of the note indicates the value of the element. Let me stop that for a moment, and this time I'll be playing a note when the elements move to the left. And I'm using a different instrument, as you can hear. And now, let me rerun that with both themes playing simultaneously. Okay, I think you have the idea there. And finally, let's look at selection sort. Here, we're playing a note when we examine one of the elements remaining. We'll use a different instrument to indicate exchanges. And finally, each time that we find the best so far, we'll indicate that with yet a third instrument. Listen to the 3 themes. The last thing that I'd like to do is to show you some of the ways that we can give data to programs in Zeus. This data form is provided by the algorithm, and we'll say that we want to run parallel quicksort on 150 elements. The views should all be familiar except this one on the right called the control panel. And the control panel is right now monitoring the values of the events that are being generated from the algorithm. Let's see, I just stopped it for a moment. The last exchange happened between elements at positions 85 and 105. Let's just go here and, let's see, say that we want to exchange between 10 and 125, and actually go and do the exchange. And if you look in all of the views, they're behaving just as if the algorithm had generated that event, just as if the algorithm were performing that action. A third way of giving data to the program is to actually go into one of the views and just, let's see, pick up one of the sticks and just go and change its value. And we can actually do that in any of the views. And if I go into the dots view, I can pick up one of the dots and change its value. I'll resume running the program. This notion of being able to edit in any of the views and have all the views be consistent representations is the basis of a multi-view user interface editor that we've built using the Zeus technology.